recording. So in our two-dimensional polar coordinates, rho and phi, what is the relation between rho, phi, and x, y? Here x is rho cos phi, y is rho sin phi. This is our polar coordinates in two dimensions. Two-dimensional polar coordinates, if you add a third coordinate z equal to z third coordinate define and that z we define it in the same way the z is defined in Cartesian coordinate system. And what does this become? This becomes the cylindrical coordinate system. Two-dimensional polar coordinates cylindrical coordinate system. What do? We simply add a third coordinate z, which is defined in the same way the z is defined in a Cartesian coordinate system. So this is the cylindrical coordinate system. Cylindrical coordinate system. And the cylindrical coordinate system, when we put z equal to 0, we get the two-dimensional polar coordinates. Two-dimensional polar coordinates to cylindrical coordinates. We will study one more coordinate system, which is called a spherical coordinate system. Confusion later. We are using rho and phi instead of r and theta. In some books, you will find r and theta instead of rho and phi. We have these three expressions. And what do these three expressions define? These three expressions, they define they define the transformation from rectangular to cylindrical coordinates. So these three equations, they define the transformation from rectangular to cylindrical coordinates. So using these three, we can define the transformation from rectangular to cylindrical. We can define the transformation from cylindrical to rectangular. So let us obtain the transformation from cylindrical to rectangular coordinates. Let us express rho and phi in terms of x and y. So let us express rho and phi in terms of x and y. So to do that, let us call this equation number 1. Let us call this equation number 2, and let us call this equation number 3. So there you go. If you take the square of equation 1 and square of equation 2 and add them, squaring and squaring equation 1 and 2 and adding. Adding a quick 1 and 2 is square tower. We get. So this will be left hand side left hand side will be x square plus y square. This is equal to right hand side. Right hand side is rho square cos square phi plus rho square sin square phi. Rho square common. So I can take rho square common, and what is inside the bracket? Cos square phi plus sin square phi. And what is the value of cos square phi plus sin square phi? The value of cos square phi plus sin square phi is, this value is 1. That's wrong. So this means x square plus y square equal to rho square. Therefore, this implies rho equal to root over x square plus y square. There you go. So row is root over x square plus y square. And this is the positive square root. Row can, and row is nothing but the distance of the point from the z-axis. And distance, as you know, distance is always a positive quantity. Therefore, when we take the square root, we take the positive square root. So this is how we express row in terms of x and y. Now let us express phi. So from these two equations, we can express phi in terms of x and y. If we divide equation number 2 by equation number 1, what do we get? Let us see. Dividing equation 2 by 1. What do we get? We get 2. What is 2? 2 is y equal to rho sin theta. And what is 1? Y is x equal to rho cos theta. So 2 divided by 1 will be y by x equal to sin theta by cos theta. Rho will cancel out. So we get y by x equal to sin phi theta. Sin phi by cos phi. And sin phi by cos phi is tan phi. Tan phi. So y by x equal to tan phi. Therefore, what is phi? Phi is equal to tan inverse y by x. This is how rho and phi are expressed in terms of x and y. Since z is already equal to z, we can simply write it again and say is equal to z. So this is question number 4, question number 5, question number 6. So equations 4, 5, and 6 define the transformation from cylindrical coordinates to rectangular coordinates. So this is transformation from cylindrical coordinates to rectangular coordinates. Rectangular coordinates. This is the transformation of cylindrical coordinates to rectangular coordinates. Next, I will discuss any point on the z-axis. Any point on the z-axis. So let us come back to the diagram again. Let me share the screen. So any point on this z-axis, z-axis the car. So any point on this z-axis, what is the value of phi? Rho is 0 tarani. If this point P lies on the z-axis, rho will be 0. But what will be the value of phi? If this point P lies on the z-axis, what will be the value of rho? Rho will be 0. And what will be the value of phi? Here, phi is indeterminate. We cannot determine phi. For points on the z-axis, phi is indeterminate. Such points are called singular points of the transformation. Such points are called singular points of the transformation. I repeat, for any point on the z-axis, phi is indeterminate, and such points are called singular points of the transformation. So we can also see from here. For any point on the z-axis, points on the z-axis already, y is 0 erni, x is 0 erni. So phi will be tan inverse 0 divided by 0. And 0 divided by 0 is indeterminate. X to y is 0 chatpa, the point lies on the z-axis. For such a point, The value of phi is indeterminate, and such points are called singular points of the transformation. Aduna cylindrical coordinates ka rectangular coordinates ka cylindrical transformation the singular point to kaina. The singular point is the z-axis. The points, what are singular points? The singular points are points lying on the z-axis. Sini first class ta say the xyz can be expressed as functions of u1, u2, u3. In cylindrical coordinates, this becomes rho, phi, and z. X, Y, Z, rho, phi, z key function on X, Y, Z. We have written X, Y, Z as functions of rho, phi, and z. And we can invert those. Invert u1, u2, u3, x, y, z key function on why we have written rho as a function of x and y, phi as a function of y and x, z as a function of z. The functions in equation 1 and 2 are assumed to be single valued and to have continuous derivatives, so that the correspondence between x, y, z and u1, u2, u3 is unique. Unique. Functions, the functions in 1 and 2 are assumed to be single valued and unique. Let me bring this again. The functions in equations 1 and 2 are assumed to be single valued and to have continuous derivatives, so that the correspondence between them is unique. But in practice, this assumption may not apply at a certain point. I repeat, in practice, such assumptions may not apply at certain points. For example, in our cylindrical coordinate system, the z-axis, any point on the z-axis, magi phi value do indeterminate level. Aduna special case ka follow pi. Okay, so let us continue. So we have done a conversion from cylindrical coordinates to rectangular coordinates. Cylindrical coordinates say orthogonal system to prove that cylindrical coordinate system is orthogonal. Cylindrical coordinate system is orthogonal and prove to prove the three coordinate surfaces. The three coordinate surfaces, they meet at right angles. They are mutually orthogonal to each other. The three coordinate surfaces, they are mutually orthogonal to each other. Sidiko orthogonal proof to hierarchy. Adriamuk any kari high cylindrical coordinate systems D. Magi unit vector unit vector so what do we do to prove that a cylindrical coordinate system is orthogonal? First, let us calculate the three unit vectors or tangent vectors. Let us calculate the three unit vectors along the three curves. So we are going to show that. What are we going to show? We are going to show that a cylindrical coordinate system is orthogonal. A cylindrical coordinate system is orthogonal. So proof se proof tawsi akoi surface sing du orthogonal oi hena proof tawsi jai aduga atopa mong amadana kona kamai tar proof tawu yagi hai kanda we find the three unit vectors along the three curves u1 u2 u3 curves to the unit vector of the theory. And if these three unit vectors are mutually perpendicular to each other, then we can say that this coordinate system is orthogonal. So to prove that, first let us consider that the position vector of any point in cylindrical coordinates is r vector. The position vector of any point we know that it is equal to xi cap plus yj cap plus zk cap. The position vector of any point in Cartesian coordinate system is xi cap plus yj cap plus zk cap. Now we can write this in cylindrical coordinates. How? We already know that in cylindrical coordinates x equal to rho cos phi. So we replace x by rho cos phi I cap plus y is rho sin phi j cap plus zd s it is zd and cylindrical coordinate system z Cartesian coordinate system they are defined in the same sense. So z remains as it is. So in cylindrical coordinates, the position vector of any point is given by this expression. Then to find the unit vectors, what do we do? First, we find the tangent vectors to the three curves. What are the three curves? Tangent vectors to the rho curve, tangent vector to the phi curve, and tangent vector to the z curve. The tangent vectors, to the rho, phi, and z curves are given by I repeat, the tangent vectors to the rho, phi, and z curves are given by, so tangent vector to the rho curves, this is del r by del rho, partial derivative. Del r by del rho. So what is the partial derivative of this? So this is r vector. So the partial derivative of this with respect to rho. So del r by del rho, it is cos phi. So this is cos phi I hat plus differentiation with respect to rho. Partial derivative phi constant rho in a differentiate over. So this becomes sin phi j hat. Z does not depend upon rho. So my partial derivative of z with respect to rho will be 0. Yeah. So this is the tangent vector to the rho curve. Similarly, the tangent vector to the phi curve will be given by this expression, and this will be this derivative with respect to phi will be minus rho sin phi I hat plus rho sin phi partial derivative with respect to phi. This will be rho cos phi j hat. Z phi will be 0. What will be del r by del z? This will be nothing but this depends only upon rho and phi. So partial derivative of this with respect to z will be 0. This also depends upon only rho and phi. So partial derivative of this will be 0. Z. So what remains is only partial derivative of z with respect to z, which is 1. So this is 1 times k. That is simply k. So these are the three tangent vectors to the row axis phi phi curve. This is the tangent vector to the row curve, tangent vector to the phi curve, tangent vector to the z curve. There go. The unit vector kay tare. The unit vectors in this direction are the unit vectors. The unit vectors in these directions are the unit vectors in these directions are number one E1. E1 the tare E row E1 is E row. What is E row? E row is nothing but the tangent to the row divided by its magnitude. So this will be del r by del row divided by its magnitude, divided by magnitude of del r by del row. This will be rho, del r by del row. So you can see what is del r by del row? Del r by del row is this. So this is cos phi I hat plus sine phi j hat. And what is the magnitude of this vector? The magnitude of this vector is sig square plus sig square plus z component square square root. So the magnitude of this is nothing but root over sig square cos square phi plus sig square sine square phi. And cos square phi plus sine square phi is always 1. So this is nothing but cos phi I hat plus sine phi j hat. Very cool. Similarly, what is the unit vector along phi? The unit vector along phi is given by, this is del r by del phi divided by its magnitude, del r by del phi. This is equal to, what is del r by del phi? Del r by del phi is this. So minus rho sine phi I hat plus rho cos phi j hat divided by root over rho square sine square phi plus rho square cos square phi. And what is this value? This value is rho square. Rho square square root over rho tare. This row and this row will cancel out. So what do we get? Minus sine phi I hat plus cos phi j hat. And what is EZ? EZ is, what is EZ? EZ is nothing but del R by del Z divided by its magnitude, del R by del Z. And what is del R by del Z? Del R by del Z is already a unit vector k hat. So this is nothing but k hat. So what are three unit vectors in our cylindrical coordinate system? The three unit vectors in our cylindrical coordinate systems are given by E rho, E phi, Ez. This is E rho, this is E phi, this is Ez. And how will we know the coordinate system is orthogonal? We'll know that the coordinate system is orthogonal if the dot product of pairs of these unit vectors are 0. So unit vectors in the dot product of the 0 target coordinate system is orthogonal. I repeat, I coordinate system is orthogonal. I coordinate curves the direction unit vectors in do dot product 0 target, we said that the coordinate system is orthogonal. So let us take the dot product of these three unit vectors. So first let us take the dot product of E rho and E phi. So let us take the dot product of E rho and E phi. So let us take the dot product. E row dot E phi. And what is E row E phi? E row. So this is cos phi I hat plus sin phi j hat. This is E row dot dot product kanaga E phi ga. And what is E phi? E phi is this minus sin phi I hat plus cos phi j hat. Select. So this is the dot product of E row and E phi. So let us open this bracket and take the dot product of each term by term. So cos phi I hat ka minus sin phi I hat ka. And is the dot product logic data. This is cos phi sin phi I hat dot C I hat. So the move siga move. You take the dot product of this and this plus cos phi, this cos phi, this cos phi, with this I hat dot this j. Minus siga move lower siga di minus la minus sin phi this is sin phi j hat dot I hat. Siga move lower plus times plus wala sin phi sin phi multiplied by cos phi j hat dot j hat. So we get 4 terms after multiplying all of this. This is equal to minus cos phi sin phi. So this is minus cos phi sin phi. What is the value of I hat dot I hat? The unit vector. Unit vector amma masama ka dot product lower it is equal to 1. So this is 1. We don't need to write 1. Cos phi I hat dot j hat. I hat is a unit vector along x-axis. J hat is a unit vector along y-axis. So these two are mutually perpendicular. So the dot product of two vectors which are perpendicular is 0. 0 tareka. I hat ka j hat ka di I hat ka j hat ka di ani di mutually perpendicular mutually perpendicular vector ani ki dot product 0 tareka. So this is 0. This is 0. Similarly, we have j hat dot I hat. This is also 0 since j hat and I hat are perpendicular. And this j hat dot j hat unit vector was hamaka dot product it is equal to 1. So it is equal to 1. So C0 sakre plus sin phi cos phi. Sin phi cos phi. This is 1. So the final answer is this cos phi sin phi plus sin phi cos phi. This will cancel out and this becomes 0. So what have we obtained? We have obtained that the dot product of E row and E phi is 0. That means the unit vector along the row curve and the unit vector along the phi curve, they are mutually orthogonal. Similarly, next we have to show that E row siga EZ. Uneasy dot product lower cell. E row ga EZ ka. So what is E row? This is E row. E row down. So this is cos phi I hat plus sin phi j hat dot with what is EZ? EZ what is EZ? EZ is nothing but K hat. This is K hat. So EZ is K hat. Here, look at this. This is I hat, this is j hat, and we're taking dot product with k hat. I hat is a unit vector along x-axis, k hat is a unit vector along z-axis, and since x-axis and z-axis are mutually perpendicular, I hat ka k hat ka dot product law 0 tare. So this is nothing but cos phi I hat dot k hat plus sin phi j hat dot k hat. I hat k hat, they are mutually perpendicular, this is 0. J hat k hat, they are mutually perpendicular, this is 0. So this is also 0. So what have we proved so far? We have proved that E rho and E phi are perpendicular. E rho and Ez are perpendicular. And what remains to be proved is that E phi and Ez are perpendicular. So E phi dot with Ez. And what is E phi? E phi is this value. This is E phi. Okay. So this is minus sin phi I hat plus cos phi j hat. And what is Ez? Ez is k hat. Ez is k hat. So this is equal to minus sin phi I hat dot k hat minus sin phi I hat dot k hat plus cos phi j hat dot k hat. I ga k ga perpendicular oi, so this is 0. J ga k ga perpendicular oi, so this is 0. So this is also 0. So what have we proved? We have proved that E rho is perpendicular to E phi. That is, the unit vector along the rho curve is perpendicular to the unit vector along the phi curve. The unit vector along the rho curve is perpendicular to the unit vector along the z curve. The unit vector along the phi curve is also perpendicular to the unit vector along the z curve. So this shows that see equation E rho, sorry, E phi and Ez are mutually perpendicular. Mutually perpendicular. Are mutually perpendicular, and the coordinate system is orthogonal. Correct. Aduna sida akoina haning is kaino akoina haning is coordinate system is orthogonal oi and proof hobusi akoina masai ki surface ahum du orthogonal oi na cut tawi machine intersect tawi haibu ma leire aduna tragasu agi the unit vectors along the three coordinate curves moi ahum si mutually perpendicular oi ragadi agi masai ki coordinate system is orthogonal oi and proof tawju ya aduna proof tawbusi ani thong tawu ya. The three coordinate surfaces, they intersect at right angle to each other and for short of ama natragana the three coordinate curves they are orthogonal to the three coordinate curves key unit vector do they are mutually perpendicular to each other and short or so yeah ko ado egati homework ama pirage homework sidi kai no hayu matamda ko hoji kari phangre. We have already obtained the value of E phi. We have already E rho, E phi, Ez. So E rho is this. E rho is cos phi I hat plus sin phi j hat. E phi is okay now. This is minus sin phi I hat plus cos phi j hat, and Ez equal to k hat. So we call this question number 1. equation number 2. This is equation number 3. What is your homework? Your homework is that you use equation number 1 and 2. Equation number 1 and 2 degi 1 and 2 seasonal, and you express I had sigi equation anis degi I had ka j had ka solve toro. You express I had in terms of e rho and e phi. Kari phangadab no when yung the horen kari phangadab no the equation 1 ka 2 which degi I had ka j had ka solve to have ni ko. From this you should get I had is equal to cos phi e rho minus sin phi e phi. J hat equal to sin phi e rho plus cos phi e phi. So what is your homework? Your homework is to start with equation number 1 and 2, and you try to obtain equation number these two equations. So you are expressing e rho and e phi in terms of I and j. So use these two and now try to express I cap and j cap in terms of e rho and e phi.